Hi, this video can be seen as a continuation of our video on complex eigenvalues and eigenvectors. Recall that complex eigenvalues and eigenvectors of a real matrix occur in conjugate pairs. This special feature leads to the following theorem, which is the main subject of this video. Let A be a real 2x2 matrix with complex eigenvalues A plus or minus IB, with B unequal to 0. Then there exists an invertible real matrix P such that A is P times A minus B BA times P inverse. The matrix in the middle is called a rotation scaling matrix. Let me explain why. The matrix A minus B BA obviously depends on the two real parameters A and B. Let's write A is R times cosine phi and B is R times sine phi, where R and phi are the usual polar coordinates of the point A, B in the plane. In terms of these polar coordinates, our matrix is equal to the matrix shown here. The part cosine phi minus sine phi cosine phi is a rotation matrix which we denote by R phi. It's called a rotation matrix because R phi times a non-zero vector x in the plane is equal to the vector which is obtained by rotating x counterclockwise around the origin through an angle of phi. Secondly, we have the scalar r in front of the rotation matrix. The product of the scalar r and the rotation matrix R phi represents the composition of a rotation and a scaling. This is why we call such a matrix a rotation scaling matrix. The eigenvalues of the rotation scaling matrix A minus B BA are equal to A plus or minus IB as shown by this calculation. So this rotation matrix has the complex eigenvalues A plus or minus IB. It turns out that conversely, any real 2x2 matrix with eigenvalues A plus or minus IB can be written as a product of three matrices with the rotation scaling matrix A minus B BA in the middle. Here's the precise formulation of that theorem. Let A be a real 2x2 matrix with eigenvalues A plus or minus IB with B unequal to 0. Then there exists a real invertible matrix P such that A is equal to P times the rotation scaling matrix A minus B BA times P inverse. Recall that we can also use the alternative form for the rotation scaling matrix in terms of the polar coordinates R and phi. So every real 2x2 matrix with non-real eigenvalues A plus or minus IB has a decomposition as shown here for some invertible matrix P. What can we say about the matrix P in that formula? It turns out that P has to be equal to a matrix which has the real part of V and the imaginary part of V as its first and second column, respectively, where V is an eigenvector of A that belongs to the eigenvalue A minus IB. Let's see how this works for the matrix shown here. The vector 2 minus I 1 is an eigenvector of A that belongs to the eigenvalue 1 minus I. This vector can be written as 2 1 plus I times minus 1 0. So the real part and the imaginary part of V are equal to 2 1 and minus 1 0 respectively. Let P be the matrix which has these two vectors as its columns. You can check that the decomposition shown here does indeed hold for this matrix P. The rotation scaling matrix in the middle can alternatively be written in terms of polar coordinates R and phi. In this example, A and B are both equal to 1, so we can substitute R is equal to the square root of 2 and phi is equal to pi over 4. Now I want to show you an example of a calculation that becomes very easy if we use the decomposition of A that we have just derived. Namely, the calculation of the 10th power of A. Firstly, we can bring the exponentiation to the rotation scaling matrix in the middle. Secondly, we can use the fact that the 10th power of a rotation matrix with angle phi is equal to the rotation matrix with angle 10 times phi, which brings us to the product shown here, which is equal to 32 times the matrix 2 minus 5, 1 minus 2. Easy calculation, isn't it? And of course the same goes for any power of A. Back to the main theorem of this video. This is a theorem about 2x2 matrices. It should be noted that rotation scaling matrices can appear in decompositions of matrices of larger sizes as well. For example, suppose A is a real 3x3 matrix with eigenvalues 4 and 2 plus or minus I. Then there exists an invertible 3x3 matrix P such that A is equal to the product shown here. The matrix in the middle is a so-called block diagonal matrix with two blocks on the diagonal, namely one scalar block corresponding to the real eigenvalue 4 and one 2x2 rotation scaling block corresponding to the complex eigenvalues 2 plus or minus I. The first column of the matrix P has to be an eigenvector of A of the real eigenvalue 4, and the second and the third column of P have to be the real and imaginary parts of an eigenvector of A corresponding to the complex eigenvalue 2 minus I. So, although A itself is a 3x3 matrix, the geometrical significance of the pair of complex eigenvalues 2 plus or minus I is still captured by a 2x2 rotation scaling matrix.